Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a second video on solving trig equations. The first one was all about the concepts before actually solving trig equations. Now we're stepping into the actual solutions, or how to solve basic trig equations. When I say basic, I mean these are equations that don't involve identities, they don't involve multiple angles, they don't involve any type of major tricks or anything like that. They're just the straightforward equations and kind of easier to solve than the others. So let's start with this first example. Find all degree solutions. So that's important here. Usually I like to have radian solutions, but in this case, I'm saying find all degree solutions. In fact, I should highlight the word all. Then limit those solutions to be only those between 0 degrees and 360 degrees. So we'll start by stating all solutions. That's usually the best technique. And then limit it down to those between 0 and 360 degrees. As mentioned in my previous video, trig equations have an infinite number of solutions. And so finding all solutions to the equation is actually going to be easier than limiting it. Anyhow, first thing you're going to do here is note you're trying to solve for theta. So let's start isolating the cosine of that theta by subtracting root 3 from both sides and dividing both sides by 2. So this just implies that, and I'll write the implication sign, that the cosine of theta is equal to negative root 3 over 2. Now I'm going to give you a warning here right now, right at the beginning. Some teachers will say, okay, and then take the inverse cosine of both sides, or take the arc cos of both sides. I am never going to say that unless we're dealing with a problem that doesn't involve a special ratio. This is a special ratio. You should never, ever, ever use an arc function or an inverse trig function when you're given a special ratio. You shouldn't have to, and it can lead to a lot of mistakes. So that is my very first warning. Now, if it's the case that it's not a special ratio, then we'll deal with that in a separate video, because there are some conditions you have to know about that really make it a dangerous activity to use arc functions, so without knowing specific details. So again, if solving a trig equation where it's a trig function of theta is equal to a ratio where the ratio is a special ratio, do not use the inverse trig function to solve. Instead, ask yourself, what have I seen that ratio before? Don't worry about the negative, and you're going to find the reference angle. So again, trig is all about reference angles and quadrants, and I have seen that trig ratio before. And so you write this triangle out. We're doing this in degrees, so I'm going to write it as 30 degrees, 60 degrees, 90 degrees, 1, 2, root 3. The cosine of what angle is root 3 over 2? Well, you can see it. Cosine of 30 degrees is root 3 over 2. So our reference angle, theta hat, not theta, but theta hat, is 30 degrees. That's our reference angle. Now we need to determine quadrants. So again, trig is just about reference angles and quadrants. In which two quadrants is the cosine negative? All students take calculus. Cosine is going to be negative in quadrants 2 and 3, because all trig functions are positive in quadrant 1, and cosine is positive in quadrant 4. So we have a quadrant 2 and a quadrant 3 angle here. So quadrants 2 and 3. So we have reference angles of 30 degrees in quadrants 2 and quadrants 3. We are ready to write our solutions. Again, Trig, specifically trig equations, is all about reference angles and quadrants. Notice I did not worry about the negative root 3 over 2 when I was talking about the reference angle. I only dealt with the positive ratio. That's always going to be the case. Always going to be the case. Doesn't matter if the trig function's negative or positive, the output. What you're worried about is what's the ratio. Not that it's positive or negative, but what's the absolute value of that ratio. And I'm going to create a little triangle, and hopefully that ratio is a special ratio, and you go through that. All right, so let's deal with the quadrant 2 set of solutions. Theta, if we land in quadrant 2 with a reference angle of 30 degrees, would be 180 minus 30, or 150 degrees. However, as we mentioned in the previous video, that's not the only way we can get to that quadrant 2 solution. We could have started, rotated over to 150, and then added 360, or 2 sets of 360, or subtracted 14 sets of 360. So our quadrant 2 solutions will be 150 degrees plus 360 degrees times k. In other words, plus a bunch of rotations of 360 degrees. And I will make a mention right now where k is in the set of integers. So it can be 0, 1, 2, 3, 4, 5, or -1, -2, -3, -4, and so on and so forth. Our quadrant 3 solution, or set of solutions, I should say, well, if you have a reference angle of 30 degrees in quadrant 3, you have gone 180 plus 30 degrees, so that's 210 degrees. And then plus 360 k. We've already written where k is in the integers, so I'm just going to assume somebody's going to go ahead and carry that over to that second set of solutions. So this is the answer to the first part. Find all degree solutions. We're done with that. Boom, I'll box that up just so that you can see it. That's a set of solutions. Then somebody says, well, wait a second. I just remembered we want the solutions between 0 and 360 degrees. Fine, let k equal 0, and you're done. So the solutions on 0 to 360, they are theta equals 150 degrees and theta equals 210 degrees. And that's just found for me by setting k equals 0. It's very quick. There you go. So once you find the infinite number of solutions, or the infinite set of solutions, then reducing it down to between 0 and 360 is just a matter of allowing k to equal 0, or it might, in other circumstances, force you to let k equal 0, 1, and 2, and we'll see those later on. So don't worry too much about that. And sorry if my screen gets wacky. Again, for some reason, it's my Wi-Fi, and I'm displaying. You don't need to know why. I apologize. As a second example, and I know it says number 4, just because it's all in the same section to me, so there were 2 examples in the previous video. Find all radian solutions to this equation, and then state the solutions being restricted to be between 0 and 2 pi. Notice this is a mixture of trigonometric functions here, tangents and sines. Luckily, it's already set to equal 0. So I'm going to use a tactic here that I mentioned in the previous video, which is factor out any common factors. So in this case, it'd be the tangent. I'll factor a tangent off that left-hand side. If I do that, I get the tangent of theta times the quantity root 3 minus 2 sine of theta, and that should equal 0. And this means we have 2 objects. We have this first object tangent times the second object equaling 0. Well, that means from our algebra that either the first object is 0, so either the tangent of theta is 0, or the second object is 0. So, or root 3 minus 2 sine of theta is equal to 0. The first one is a case where you're dealing with a ratio, 0 specifically, that is a special ratio, and I can easily find out what angle I'd plug in the tangent to get an output of 0 by graphing the tangent very quickly. The tangent graph looks like the following, and it goes on forever, right? It repeats this pattern. There are vertical asymptotes at negative pi over 2 and positive pi over 2. I don't actually need to graph all of this, but I just need to be able to get an idea of when the tangent becomes 0. And you could see just from the tangent graph, it becomes 0 at 0. Also, it becomes 0 because tangent's period is actually pi. That's very important to note. It becomes 0 again at pi. So every pi, it'll become 0. So the solution to this equation is theta is equal to 0 plus any additional step size of pi. Now, obviously, you don't have to include the 0 in that. So I would just say this implies that theta is equal to pi times k. And again, k is in the integers. And then I move over to the other equation. So this is my first set of solutions. Now I go to the other equation. Notice I didn't also bother to write out quadrants or reference angles. There was no need because tangent to theta equaling 0, 0 is a quadrantal ratio, a ratio from a quadrantal angle. And so that's why just drawing the graph is good enough. Going over to the second equation, if you maybe move the 2 sine of theta over to the right hand side and then divide both sides by 2, you'll get the square root of 3 over 2 is equal to the sine of theta. That is a special ratio. And you get so used to drawing out the triangle, here the pi over 6, pi over 3 right angle, that it just occurs over and over again. I should copy and paste that, and that way, or at least copy that. That way I could just paste it in every problem from this point forward. Now, looking at the sine of theta equaling root 3 over 2, that theta would be pi over 3, because the sine of pi over 3 is root 3 over 2. That's our reference angle. So theta hat, our reference angle, is pi over 3. Then we ask, because this is positive, what quadrants is the sine positive in? Well, that'd be quadrants 1 and 2. So we have a reference angle of pi over 3 in both quadrants 1 and 2. So I know that my actual angles, and I usually do it this way where I say, well, the quadrant 1 set of solutions, my actual angle is going to be pi over 3, because that's the actual angle with a reference angle of pi over 3 in quadrant 1. But then plus 2 pi k. And in quadrant 2, my set of solutions is going to be theta equals, again, quadrant 2 with a reference angle of pi over 3, my actual angle is 2 pi over 3 and then plus 2 pi k. And you are now looking at, in boxes here, the 2 set of solutions. Sorry for the ink off to the side. I pasted in something I didn't mean to. It's for calculus. Anyhow, so we have our our solutions. It's actually a bunch of different solutions, right? But those are the infinite number of solutions to this equation. What if we want to restrict those to just be solutions between 0 and 2 pi, including 0 and 2 pi? Well, we have to go through each of these. I can't just say let k equals 0 and be done with it here, because k equals 0 would give me 0. That's perfectly fine. So maybe I should say on 0 to 2 pi, theta, the solution set from here, if you let k equal 0, you get 0. Or theta could be, if you let k equal 1, you'd get pi, and that's between 0 and 2 pi. If you let theta or k equal 2, you get theta equals 2 pi. So notice letting k equal 1 was just not enough. So you generally start at 0 and then work your way up until if you go any further, you'd be outside your given interval. So if I let k equal 3 right here, then I would have 3 pi, which is not within our interval. So I just stop right there. So on 0 to 2 pi, those are the solutions from that tangent. And then also from this on 0 to 2 pi, I'll start with k equals 0. So theta equals pi over 3 and theta equals 2 pi over 3. And if you try to plug in k equals 1 into these formulas, you would rotate by 2 pi. So you'd get outside of 0 to 2 pi. So you're pretty much done listing these equations or these solutions on 0 to 2 pi. Let me box up the other one. Oh, I already did. All right. So we have solved this trig equation. Not too terrible. Moving on and really trying to showcase all the different kinds of equations you can see, at least the basic level. We have 2 sine squared of theta plus 1 is equal to 3 sine of theta. And we want all radian solutions to this equation, and then we're going to restrict it down to just being solutions between 0 and 2 pi. Well, if you take a look at this, this is going to be quadratic. It's sort of like somebody saying solve 2x squared plus 1 is equal to 3x. You can totally move that 3x to the other side and factor. So that's what I'm going to do here. Let's say this implies that we have 2 sine squared of theta minus 3 sine of theta plus 1 is equal to 0. And that quadratic is factorable. Just group it up like this, say equals 0. We have 2 sine of theta. Here we'll have a sine of theta over there. Need this to be a 1, this to be a 1. They're both negative. Let's just double check. If you try to distribute things out, you'll get 2 sine squared, which is exactly here. This negative 1 times negative 1 would give me the positive 1, so that's done. And then minus sine minus 2 sine gives me a negative 3 sine. So that is the factorization. So 2 objects multiplying to become 0 implies either the first one is 0, in other words, sine of theta equals 1/2, or the second one is 0. In other words, sine of theta is equal to 1. So you have those 2 possibilities. Notice you're now solving 2 trig equations. That's just how trig equations work, is that you work down and then all of a sudden you're now solving more trig equations than you originally started with. Well, such is life. One of these, this first one specifically, is a special ratio. So let me go ahead and paste in what I said I was going to do earlier. So I pasted in my special triangle there. And I can easily see the sine of pi over 6, whoops, need ink, sine of pi over 6 is 1/2. So I know my reference angle is pi over 6. Again, reference angles in quadrants. The sine is positive in quadrants 1 and 2, so I'll just write it that way. So let's go ahead and finish solving this equation by finding all of its solutions. The quadrant 1 solutions, well, theta is going to be pi over 6. But remember, we want all solutions, so I'll say plus 2 pi k, pretty easy. And the quadrant 2 solution, well, again, reference angle is pi over 6, so 5 pi over 6 in quadrant 2, plus 2 pi k. Again, in both cases, k is just an integer. So I just throw that in at the end there. So those are the infinite number of, those are the infinite set, or that is the infinite set of solutions for this first factor. Now we go to sine of theta equals 1. And as I've mentioned in the previous video and a little bit in this video, when you have the sine and the cosine, they equal 1, -1, or 0, then your angle is a quadrantal angle. You're not going to have a special triangle for that. So you're going to have to be able to quickly graph out the sine curve just to see at what angle is the sine 1. And you can see the sine is 1 at pi over 2. Remember, sine starts at 0, 0. So I know that my angle is pi over 2, and it'll reach that height again every 2 pi thereafter. So this one is real fast to solve if you know the graph of sine. It's just going to be theta equals pi over 2 plus 2 pi k. Technically speaking, pi over 2 is not a reference angle because it's equal to 90 degrees, and reference angles are always acute. So I wouldn't call that a reference angle, but I wouldn't dock somebody if they did call it that. Now, we're being asked to reduce that down to solutions only between 0 and 2 pi. Well, in both cases, I'm just going to let k equal 1. Or 0, I'm sorry. Let k equal 0. So on 0 to 2 pi, the set of solutions is going to be theta is equal to pi over 6, 5 pi over 6, or from this one right here, pi over 2. If you try to let k equal anything other than 0 in any of those equations, you will end up with angles outside of the interval from 0 to 2 pi. So this one is completely done as well. These go very quickly if you are comfortable with what you're doing. And to be comfortable, I mean, you really have to know your trig ratios, you have to know your trig graphs, the sine and cosine, and you have to know your algebra to be able to factor. And you also have to know reference angles and quadrants. Basically everything you've learned up to this point, you have to have mastery with to be able to zoom through these problems. Now this is an interesting one. I really like this problem on many different levels. The cosecant squared of theta minus 4 is equal to 0. This can be solved several different ways, to be honest with you. And we're not told how to solve it. We're just saying find all solutions. I am going to solve this using radian measure. In your course, your instructor might tell you that you should always assume your angles are in radians, or they may say, I don't care, just answer the question. So whatever, I'm just going to answer this in radian measure. All right, two ways to solve. You could either just add 4 to both sides and take the square root, which is probably the way I would normally do this. So add 4 to both sides and then take the square root. The problem is when you take the square root of both sides, we know from algebra this will be a plus or minus. When you take the square root of both sides of an equation, well, maybe I shouldn't say it that way, but if you have an unknown squared and it's equal to k, when you take the square root of both sides, that unknown is plus or minus the square root of k. So we have an unknown squared, the unknown is cosecant, and when you take the square root, you get the plus or minus. So that's one way we could start the solution here. The other way, if you're curious, I don't know if anybody is, but another way you could do this is you could see this is a difference of squares. It's a cosecant squared minus 2 squared. And so you'd have a cosecant of theta minus 2 times a cosecant of theta plus 2 is equal to 0. Or in other words, cosecant of theta is equal to 2, or cosecant of theta is equal to negative 2. Notice you get the same answers. Cosecant is equal to plus or minus 2. Okay, so both of them are saying the same thing. Now, when you're working with a reciprocal function like a cosecant, a secant, or a cotangent, once you get to a step like this, take the reciprocal of both sides, just to rewrite it in terms of the base function. So this would imply that you're dealing with the sine of theta equaling 1/2, or the sine of theta equaling a negative 1/2. You would do the same thing over to the right hand in this one had you done it this way. You just break that into these two equations, and again, we're at the same spot. I will find the reference angle for sine that gives me an output of 1/2. Let me go ahead and paste in my triangle there. Sine of pi over 6 is going to give me an output of 1/2. So in both cases, actually, my reference angle in both cases is pi over 6. However, if you look at the ratios, I have a positive and a negative ratio. So if I ask where's the sign positive, you would say quadrants 1 and 2. And then I'd say, oh, by the way, where's sign negative? And you'd say, oh, and 3 and 4. So essentially, I have 4 quadrants worth of solutions, all quadrants. So let's go ahead and just list out all of the solutions, basically every single quadrant's worth of solutions, right? Quadrant 1 solution, reference angle of pi over 6. The actual angle is pi over 6 plus 2 pi k. Quadrant 2 solution, reference angle of pi over 6. The actual angle is 5 pi over 6 plus 2 pi k. Quadrant 3 solution, reference angle of pi over 6 means the actual angle is 7 pi over 6 plus 2 pi k. Notice I'm assuming that you know reference angles because it's been quite some time since we've learned that stuff. So quadrant 4, reference angle of pi over 6. Actual angle is 11 pi over 6. And again, plus 2 pi k. There we go. Those are all the solutions, and that's what we were asked to find, is find all solutions. We are done. Pretty nice. Again, very fast if you're confident with your algebra and your reference angles and all the stuff we've done in trig up to this point. Now this one's on the verge of not being a basic equation, but I like it so much, I'm going to pretend as though it's a basic equation. Notice we constantly deal with the ratios of 1/2, root 3 over 2. I've yet to put in a 1 over root 2, but I have an example later on with that. But we're dealing with our special ratios. You just see them over and over again. It becomes kind of a knee-jerk reaction. You can totally be an expert with all of these ratios within like a day of doing problems. A lot of students would probably look at this and freak out. They would look at this and go, oh wait, I should use a sum of angles identity. No, you shouldn't. Do not use a sum of angles identity here, because if you tried to use a sum of angles identity, you would have the sine of A times the cosine of 50 degrees, and you don't know what the cosine of 50 degrees is, plus the sine of 50 degrees, which you don't know what the sine of 50 degrees is, times the cosine of A, and you would be locked. Equals, by the way, root 3 over 2. You would be locked. You wouldn't be able to do anything here because you don't know the sine and the cosine of 50 degrees. So I highly recommend that you do not split this up. If you just have a single trig function equaling a ratio and the ratio is special, then trust me, you know what to do. You just don't know that you know what to do. But I'm going to start by saying, well, what is our special triangle? There it is right there. And what would I plug into the sine normally to get a root 3 over 2? Sine is opposite over our hypotenuse. So sine of, we're going to do these in degrees. So it's going to be actually sine of 60 degrees is root 3 over 2. So I know that my reference angle is 60 degrees. But is that the reference angle for A? Absolutely not. It's the reference angle for this highlighted angle. I don't know what that angle is. I mean, we do, it's A plus 50 degrees, but the reference angle, I'm going to write this way. The reference angle, A plus 50 degrees hat, is 60 degrees. Again, because the sine of 60 degrees is root 3 over 2. So that entire picture, just think of it as a picture. That picture has a reference angle of that picture hat equaling 60 degrees. Then you ask yourself, where is sine positive? Well, it's positive in quadrants 1 and 2. Okay, well, our quadrant 1 solutions then should be that angle. Maybe I should not say that angle. I should say that angle. Zoom out. A plus 50 degrees. Let's see. I have a reference angle of 60 degrees in quadrant 1, so the actual angle is 60 degrees, and then plus 360 degrees K. In quadrant 2, don't worry, I'll go back to that problem in a moment. Our angle, which is A plus 50 degrees, because that's our angle. Well, let's see. We have a reference angle of 60 degrees in quadrant 2. 180 minus 60 is 120. So our actual angle in quadrant 2 is 120 degrees, and again, plus 360 K. But we need to solve actually not for the angle, but for A. That's actually what is the implication is. The implication is solve for the unknown, not just for A plus 50. So we'll go ahead and subtract 50 degrees from both sides of each of these equations. If I subtract 50 degrees, I'm just going to subtract it from these numbers right here. So A is equal to 10 degrees plus 360K. And A is equal to 70 degrees, and again, plus 360K, where K is an integer. I'll just write that off to the side just so I have it kind of complete in there. But that's how you would do a problem like that. It's actually pretty cool. It looks more complicated at the beginning than it really is. You just treat it like it's some picture. You can call it theta if you really wanted to, and just deal with theta hat, and then in the end say, oh wait, it wasn't theta, it was a plus 50, and then solve for a. So that's how this problem is done. Very, very nice problem. I dig this problem a lot. And here's the final example in this video. And this is more of a precursor to what we're going to see in future videos, but it's good to get it early on just to kind of see what goes with how we would approach this. So you should note, this is definitely quadratic, right? It's quadratic in form because it looks like an x squared minus x minus 1. However, you could not factor this. This is a prime polynomial. It does not factor. So how are you going to deal with it? Well, just like if you were asked to solve x squared minus x minus 1 is equal to 0, you would use the quadratic formula. X is equal to 1 plus or minus the square root of 1 minus 4ac, right? All over 2a. So that's what we're going to do here, is we're going to go ahead and do the same same idea. In fact, we kind of just did, right? We took the opposite of b, plus or minus b squared minus 4ac all over 2a, but instead of x equaling that, it's actually sine of theta that equals that. And so now we have what our solution, well, what our ratio looks like. Sine of theta is equal to 1 plus or minus. That's going to be the square root of 5 over 2. And actually, I like this example for a couple reasons. One, you have to use a quadratic formula to get at least to this point. But we're not done, right? You want to find the angle theta. Well, this means you have two possibilities. Either sine of theta is equal to 1 plus a root 5 over 2, or sine of theta is equal to a 1 minus a square root of 5 over 2. Here's where being very careful with your work is important. Keeping an eye out on what you're doing, kind of keeping a logical mindset the entire time is very important. I hope you would agree that the square root of 5 is greater than 2. Greater than 2. That's because it's greater than the square root of 4. And the square root of 4 is 2. So that's greater than 2. So we have 1 plus some number that's larger than 2. So that numerator's larger than 3 being divided by 2. In other words, this is greater than 3 halves. Can sine actually be bigger than 3 halves? No. There's no solution to this part of the equation because sine of theta is between, always, -1 and 1. And unfortunately, in this case, we have a big issue. Our sine of theta, in this case, would have to be, if there's a solution, would have to be bigger than 1.5, and that's outside of what the range of the sine is. So there's no solution from that. That is a great, fast way to showcase, oh, there's no solution to this. Now let's take a look at the other equation. And this one actually might have a solution. That's like 1 minus something slightly greater than 2, but not 3. So like that might be a 1 minus, let's say 2.1. And if that's the case, that's going to be a negative 1.1 over 2, which is still less than 1 in magnitude. Okay, or less than 1 in magnitude is correct. Now the reality here is you're going to have to use a calculator for this because this is not a special trig ratio. Because of that, I'm going to approximate the value that you're seeing here. This is roughly equal to, I don't want red, I want black here. It's approximately equal to a negative 0.618, and it goes on forever. And in fact, I just want to let you know, the absolute value of that is the reciprocal of the golden ratio. Kind of neat. It's also the absolute value that's 1 minus, or the golden ratio minus 1. In fact, this is 1 minus the golden ratio. So there you go. Anyway, doesn't really matter. What is important though is that we know approximately what the size of this is. So this is somebody asking us solve sine of theta is approximately equal to negative 0.618. Now, to solve a trig equation that doesn't have a special trig ratio, what we're going to do is grab a calculator, but we need to find the reference angle first. And here is a critical warning. When you find the reference angle, always find the reference angle for the positive ratio. Notice every time that we've done a problem in this video and I've said, what's the reference angle? I've never said, what's the reference angle? How do we get a negative root 3 over 2? I've always said, how do we get a root 3 over 2? I don't care about the negativity of this number. So when you find a reference angle using technology, use the inverse trig function of the absolute value of the ratio. In other words, just rip off the negative sign off that negative 0.618. You would just find the sine inverse of 0.618. Let's go ahead and showcase how that's done. I just need to see, we're going to be in degrees. So I'm going to hop over to Desmos and share my screen, and I'll showcase what I mean here. So I'm in the scientific calculator in Desmos, just because I want to. I'm in degree mode. If you're not sure if you're in degree mode, just type in the sine of 30. It should be a half, and it is. So we know we're in degree mode. I'm also going to go ahead and use the exact value of that 1 minus the square root of 5 over 2. Just because I want to get as an exact value as possible. I'll call that C. C is equal to that. All right. So now what we're going to do is we're going to find the arc sine of not C, but the absolute value of C. So I think I could just do it this way. Absolute value of C. And it gives me roughly 38.2 degrees. If you did it with just C, not the absolute value, it would give you a negative angle. And I'm just going to tell you that it gets even worse if you're dealing with the arc cosine. So don't find the arc sine of the positive value. Find the arc sine, arc cosine, arc tangent, whatever you're using. Find it of the absolute value of whatever your ratio is. That's critically important. That's our reference angle. And there I've written it in. Theta hat is the sine inverse of the absolute value of that 0.618, which is approximately 38.2 degrees. Remember, we're dealing with this problem in degrees, so let's go ahead and do that. And to finish this out, let's see. The sine is negative. Where is the sine going to be negative? Well, quadrants 3 and 4. So we know we have that reference angle in quadrants 3 and 4. This is a very robust example because it involves the calculator. And I'm just letting you know, I have calculus students that will ask me why, like they're doing work in an online program and they're getting things wrong. And they're like, why is that the case? And it's because they're using the arc sine or sine inverse or cosine inverse or tangent inverse to solve their problems when they have problems that don't, that involve special ratios where they don't need to use the arc sines and stuff like that. So you only want to use the arc sine, arc cos, and arc tangent if you have a ratio that's not a special ratio. So this one required a calculator or it has a decimal approximation, so it's not a special ratio. And let's go ahead and list out the actual angle. So remember, I don't need to actually do the plus 2 pi k here because, or plus 360k, because we want our solutions just from 0 to 360 degrees. So I'm only going to just list out the angles between 0 and 360 here. The quadrant 2 or 3 solution, sorry about that, is going to be theta is equal to, well, I'm in quadrant 3 with a reference angle of 38.2. So that's 180 plus 38.2 degrees. What is that? 218.2 degrees? Approximately, by the way. 218.2 degrees. Let's see, 20, 10, 8. Yep. And in quadrant 4, our angle is 360 minus the 38.2 degrees. And that is going to be 321.8 degrees. Let me just double check that. 59, yep, 60. Okay, 321.8 degrees. So those are our two solutions to the original equation. Those are the only two solutions, 218.2 degrees and 321.8 degrees. This is a good example just because it showcases what we have to do when we use technology. I'll have another video at the end of the series just dedicated to technology and solving trig equations. But most of your solutions for trig equations are going to be done by hand without even touching a calculator.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.